Good morning, all. So I'll start. The presentation is loading, I think. So thanks GT for inviting me to present the keynote today. I think there are 2 days exciting presentation lined up for the upcoming sessions. So I stand before you to talk on the topic that resonates deeply, the transformation shift towards electric vehicle, which is the leveraging system simulations for EV revolution. Before going into the topic, I just want to give a heads up about OLA. OLA, we started from a ride-hailing company. We redefined the ways that million people commute to the cities through just a press of a button with a ride-hailing platform. From there, we thought of building the sustainable future for the world from India. That is the key initiative began starting off OLA Electric. In OLA Electric, we have started our Gigafactory, the OLA Future Factory, which was groundbreaking at March 2021, and we sold the first vehicle in December 2021. Along with that, we understand that the cell are the key art of electric vehicle. We also have our world's largest battery innovation center, and along with that, we will be making our Gigafactory operational by 2024. With that, we wanted to make EV revolution across the globe. We wanted to build the product for the world from India. This is just a glimpse of a future factory. This is spread across 400 acres in Pochampalli in Tamil Nadu. So this is a completely automated manufacturing facility. So this video, many of you might have seen this video online. Just wanted to run it through. This is a battery line which is completely an automated process from cell placing till EOL testing, and also there are well lines which you will see in the coming videos where it is all automated. So you see the well line is also completely automated in our plant. To just keep the time, I just skip this video. This video is online available. So before starting a presentation, I want to say about the growth of EV in India and the globe. In 2022, the EV was just 1% across the globe. But we see a drastic growth in the recent years. It has increased 6 times, and now we see a EV penetration of 6% across the world. In major urban cities like Bangalore and Pune, we see close to 20% of the vehicles are already converted into EV. EV revolution is not only happening across urban cities, but also we see pan-India. OLA Electric contributes to 25% of the EV electric vehicle scooter which are sold last year in the country, and we are close to 40% market share in the recent months. So why the future is towards EV? There are close to 40 lakhs Indian purchasing two-wheeler every year. India is mainly thriving on humans which thrives for two-wheeler for the day-to-day commute. Comparing EV to traditional petrol vehicle, they have a very less maintenance cost. Basically, they are 1/10 of the cost of a traditional ICE vehicles. So when we see that there are some barriers around the EV in order to adapt it. One is the range anxiety. The other one is the charging and the charging infrastructure around the EV. And the last one is the life or the life of the battery of the electric vehicle. So with OLA, we want to break these barriers. So we are planning to have 10,000 plus charging stations in India within less than 3 months, and we have a variety of products ranging in OLA which starting from 79,999 to all the way to 1,45,000. This helps us to have a variety of products, and we also have the charging infrastructure in place, and we also have a very good warranty for our electric vehicles. So with that, we will be able to break the barriers of electric vehicles so that we will be ending the ICE. So next I want to talk about the system simulation, how system simulations help in EV revolution. As we stand in the forefront of EV revolution, system simulation helps to address some of the most pressing challenges of EV. Basically, the interaction effect of different systems, how they operate in an electric vehicle. The main components of an electric vehicle are battery, as you know, the motor, the controller, and the charging system. These multiple systems need to interact with each other in a seeming way in order to give a good performance and also with an optimum efficiency. There are multiple modeling needs to be done on the battery simulation. For example, we'll be able to model the SOC, state of health. When you come to motor and powertrain simulation, we will be able to model the torque, efficiency maps and other things. And also when you come to charging simulations, we'll be also able to do an optimum charging algorithm for the model. And also we'll be able to deploy a charging strategy, how we will be able to have multiple charging locations across the globe. So basically, the other areas where we are targeting on the system simulation is the thermal parts. So in an EV, thermal is really important parameter which we have to take into consideration. In the growing trend of system simulations, we will be able to model each and every parts of the thermal. For example, the battery cooling system, the control logic on the battery, the cooling system of the motor and the powertrain systems, and also the cooling system of the charging. So with the help of these system simulation tools, we'll be able to make many of the parametrics model. So we need not develop each model from the scratch. We'll be able to use the previous models and also develop upon this model and can create this model into a parametric model which reduce a lot of development time. And we'll be able to also use different types of data we can be able to feed into this model. For example, a different type of charge or discharge cycle. And then from that, we'll be able to identify the exact use case of the customer and develop the system for those customers. And these models, with the growing trend in the connectivity and the data which is available across the globe, so we'll be able to tune these models with the real-time data. Once these models are being tuned, they can be scaled and used to validate for the future products. So simulation areas. So here I want to talk about how we are trying to model different subsystems of a component. As I said, in a system simulation environment, we'll be able to understand the physics and mathematical models which are interacting between each other. From thermals, from electrochemical to electromagnetic, from power electronics. So when these systems are coherently in place, when we are trying to simulate using the system simulation tools, they will be able to leverage these model capability into control logic development for these model, and also understand in the dependency between the various subsystems and also the counter effect of these on vehicle performance. Thus, we will also be able to run a fast running model with these system simulation tools, which also helps in reduce the time to development of the project, which is very keen in this developing country. So I would like to touch upon some of the simulation methodology we currently follow. The first one is the input data collection. This input data collection is basically the gathering requirements which we need to do our starting phase of a simulation, where we try to collect a lot of data which required to model the systems in place. Next, once these data are collected, they are modeled with different types of approach. We use, the trend of the globe is on AI and ML. So AI and ML, we use these technology in order to fuse the physics and mathematical model into the system in order to address this approach. Once these models are developed, we need to calibrate these models before putting them into real use. Then comes the calibration of this model with real-time data. So when these models are developed, there are previous historical data available with us from the real world scenarios. So we'll be able to train these models with these real-time data, which will make the model more robust and more predictable. Once these models are trained with this real-time data, we run some actual validation test case in order to validate these model and make sure their results are actually matching with the model simulations. Once these are done, these model can be deployed also for the future use, not only for the current understanding. These models are saved in our data lakes or data platforms, where we'll be able to track this model in the future, and we will be able to understand and use this model and leverage them for our future products. So in this slide, I would like to talk about different areas where simulations are being used or in place. The first one is the right sizing. Right sizing is basically what I mean by here is sizing of the exact component of battery and motor for an electric vehicle. For example, different customer has a different requirements of range, and different customer has different requirements of performance from a vehicle. So in order to manage both, we need to size each of every component of an electric vehicle properly. That is what we do with these right sizing tools. We try to understand the customer requirements, Once the customer requirements are understood, then we try to model these in system tools, which will be able to predict what battery or what motor is required for the customer needs. Then comes the thermal simulation. In thermal simulations, basically in an EV, there are a lot of elements which are emitting heat. So thermal simulation is one of the critical parts in an EV development process. So one such is that there can be heat generated from the cell in the battery. There is also heat generated from the power electronics. There are also the heat generated from the motor, the charging systems. So we need to understand the different system, how they are working coherently with each other. So with these thermal simulations, we will be able to identify the control logics and control algorithm which we need to be done on the vehicle in order to improve the thermal of the vehicle. Also, we will be able to identify the novel solutions of cooling which can be deployed in the electric two-wheeler. In the upcoming sessions, my team will present about one of the topic which we have done. We have identified a novel methodology of cooling system for battery cooling with the help of GT. That will be presented in the afternoon session, I think. And next comes the battery electrochemical modeling. When I say battery electrochemical modeling or cell modeling, there are multiple things which is involved around the cell. The first point, which is the cell performance. As an electric vehicle, battery being the heart of the vehicle, we need to juice out every point or every performance from the cell. This we'll be able to identify by modeling these things in an environment where we'll be able to understand the performance of the cell and push the cell to the limits. So next, the complicated point in cell modeling is the aging. There are two types of aging in cell. One is the cycle life, another one is the calendar aging. From the cycle life perspective, we'll be able to at least do quick charge and discharge of the cell in order to identify the cycle life. But when we comes into the calendar life, it is a very complicated process. For example, if we have to provide a warranty for a customer for a prolonged time, we need to find out how the cell is aging for its lifetime. So these things, in order to do a real world testing of these calendar aging, it takes immense lot of time to understand and derive from this. But with these system simulation tools and trends, for example, I want to point about a live case what we have done at OLA with GT Suite. So GT Suite auto-lion model we have built for our battery pack through the electrochemical modeling. With this modeling, we were able to understand the cycle life and calendar life for the cell. So once we have built this model, we validated for a few test cases for a few life cycles of the cells. And these model, what we have developed, has been used to train our AI and ML algorithm, and we found out a fusion technique. With that, we were able to predict each and every customer's SOH which we have in the field. And once we are able to predict this, we also can predict the future of the SOH, how this trend is moving in terms of its aging. So with that, I think OLA has recently launched an 8-year warranty program for the battery. I think no OEM would have dared to announce this. And also even the ICE vehicle does not have this much prolonged warranty for their product. With that confidence of our modeling tools and capabilities, we were able to achieve this and we are able to provide this to our customers. So we also have a detailed session about how we use the GT Suite in order to build these auto-lion models and how we optimize the charging algorithm and how we shape this charging algorithm in order to require for a different customer needs in our upcoming sessions from my team. So and also next is the predictive control. When I say predictive control, there are a lot of data stores, AI and predictive maintenance algorithm which have been developed in the course. Everywhere we hear the topic called digital twin or data and AI ML. So I would like to talk more on the predictive control in my upcoming slides where I will present about my digital twin model which we have recently deployed in OLA. And next is the co-simulation. So in the co-simulation, basically in the growing environment, different simulation engineers use different tools in order to model their components. For example, a guy can use a different CFD tool or for example, a control engineer can use a MATLAB for doing a different control logics. When it comes to co-simulation, we will be able to use all this into a single platform. We also use GT in order to do multiple co-simulation, and also we try to use it in order to derive our control logic from GT, and then post that these control logic can also be deployed in the field with our OTA capabilities. The last point I want to cover over here is on the data asset and the boom in simulation. With the growing data available with us, the data will be a great asset and boom in the simulation field. So with this data, we'll not only be able to train a model, we'll also be able to understand a model and predict a model in a better way. So I want to present over here the case study what we recently did about a digital twin, which we are deployed in each of our two-wheelers. So what do you say? What do you understand about a digital twin? A digital twin is a replica of the customer vehicle or the customer scooter on a cloud or a different environment, where we are able to model the complete behavior of the vehicle in a different environment to understand and predict the behavior of the scooter in a real time. So there are different models which we have deployed in the cloud in order to understand and predict these real-time models. These models are based about AI, ML, and also we have models with physics-based and mathematical-based. With these models, we'll be able to predict the real-time vehicle performance. We'll be able to also predict the predictive maintenance requirement of the vehicle. And then with these capabilities, we can also adapt the control logic which we need to be used on the vehicle in order to tune the models. So once these control logic are being used, we can have a continuous improvement of the vehicle. The vehicle is not become a stationary one. So we have a continuous improvement roadmap which we plan on for the vehicle for the customers with the help of these capabilities. So through this, we'll be able to achieve quality, accuracy, reliability, and customer satisfaction. So how we end up building this model? So our digital twin model of our customer vehicle is built from the customer data. Our scooter is connected across the cloud. So our scooter sends every data. For example, we get the battery management system data. We also get the telematics data of the vehicle control unit. We also get the motor control unit data. With these data, we will be able to we will be able to collect critical information of the customer scooter, and these data have been used in our simulation or modeling technique in order to predict or run the real-time vehicle in a cloud environment. Once we have the customer data, the next part is how do we deploy and do a real-time model running over the cloud. So we try to model a vehicle in the cloud where we will be able to run the data of the customer at different vehicles, and we will be able to predict the output of these vehicles. Once these predicted output are there, for example, if you run 500 test cases and get 500 types of different use case and run on the model, we'll be able to get these varieties of combinations. Once these varieties of combinations has been done, these models we train using a technique by a fusion model or a LLM models in order to drive this into real-time models which run on a real-time at a faster pace in the cloud. These models are deployed again in the cloud, which replicate the direct of a two-wheeler, which helps us to predict any of the anomaly in the vehicle because of any over battery temperature rise or any overcurrent which has been taken from the battery. Once we are able to predict these anomalies of the scooter, we will be able to come up with algorithms in order to prevent them, either through software or we can do a predictive maintenance by proactively calling these customers back, thus reducing the stagnant time of these electric two-wheelers on the road. And also, as I previously said, we used these digital twin model in order to predict the SOH of a scooters. So with that, we'll be able to not only predict the current state of health of the scooter, we'll be also able to predict the future of the scooter. Down the line, how the customer behaves. Based on the customer behavior, we'll be able to also understand how these trends are going to change. We'll be also able to shape the charging behavior and discharging behavior required for the vehicle with this model. For these things, we need not even go to the customer. With our OTA and the cloud connected capabilities, we will be able to deploy these things on the customer scooters within no time. So the benefits of digital twin. The digital twin, what we have built is more automated way, which uses informed decision making in order to do a real-time predictive insights of the vehicle, thus helping us to save a lot of time and cost over the model. In a digital twin, we predict currently we have multiple areas where we have developed a digital twin. One such area is the SOH estimation. And also we do a predictive maintenance and a continuous improvement of algorithms which we use in our two-wheeler and other vehicles. And also we predict the wear and tear of components like a tire, brakes, and proactively inform the customer about these wear and tear and get these components changed. This is about the presentation on my digital twin. So I'd like to touch upon the final topic, the advantage and benefit of the simulation. So as I said, there are a lot of areas where the simulations is growing. The system simulations is growing to an enormous level in order to meet the technology rise, in order to compete with the globe. So one such area is there is a lot of advantage we see is the future prediction. Future prediction, when I say with the available data of the current state, we'll be able to predict the future, what the customer requires down the line 10 years from now, how the customer's range is getting used. For example, what type of battery pack or capacity will be required to use it for the customer in order to suit a variety of customer requirement. We try to tailor-made a solution in order to meet multiple customer requirements. In this, we'll be able to predict the future, and also we'll be able to understand how the customer behavior is changing, and then we'll be able to develop new systems and new models in order to suit the future trend of the customer requirements. Next is extreme test condition and validation. When I say extreme test condition and validation, India is a diversified in geography. So we have vehicles, if you are going to sell vehicles in India, we need to design vehicles to run it in Leh Ladakh, which is at -10°, and also at Jaisalmer, which is at 50°. So, and also there are different types of customer in India. So if you say, when I say different types of customer, we have customers we are running at a very low speeds, like at 20 or 10 kmph at an average speed, which operates the battery pack or vehicle which are at a very low C rates of 0.2 or 0.3 C. And also we have customers who are driving our vehicles in an hyper mode at an aggressive speeds, which pushes the cell to the limits. So we need to validate all that conditions, which will become very difficult in a real world condition. In that case, these simulation tools helps us to validate all the corner cases of our vehicles in order to have a very good product for the customers. And also one such example I like to highlight is when we end up for a controller development. When we do a controller development, there are a lot of areas which are unknowns. For example, how the customer is going to drive. He's going to drive downhill, uphill, like a slippery road, a muddy surface, and also how the throttle input is going to the vehicle from the customer. And also we have a variety of parameters like at various SOC or state of charge he is driving these vehicles. In order to understand this behavior and do a real world testing, there will be millions of test cases which is required to be run. So when doing these kind of test case, we might miss out some of the corner case testing. But with simulation and with systematic approach, we'll be able to jot down all the test case in place. So once we have jotted down all these test case in place, we'll be able to run all of these in the virtual environment with the help of multiple simulation tools. We can build these models together, and thus we'll be able to cover all the corner case testing of the vehicle. The last comes like the time benefit and cost. As you all know, with the help of simulation, if you are able to make a very robust model in the simulation tools, in the future we might even skip the physical testing or reduce the physical testing. So this is a great advantage which we get from simulation, and also with the help of more real-time data piling up. So there are a lot of areas where we will be in the future we might even skip the physical testing and rely more into simulation. Thus we will also be able to eradicate a lot of physical and rigorous testing, and thus we'll be able to have more cost saving into a product, and then we can have a better product to the customers. I like to summarize the topic by pointing out three key things which is currently being growing. One is digital twin, which I already spoke about, how we are using digital twin models, how we are using a physics-based, mathematical-based, and also a fusion technology in order to derive these digital twin models, and we have deployed these for all our scooters and all our customers. The next point is how we end up in predicting the range, predicting different types of behavior of the customer. When I say predicting different types, in simulation tools, we have tools lasting from variety of domain, from electrochemical to electromagnetic. We can do what not in simulation. So this is a very key area which everyone needs to know and grow upon it. With these simulations, we will be able to move most of our testing into it and most of the initial product development into the simulation phase. The last is continuously optimizing and improving the accuracy of our model. When I say continuously improving the accuracy of the model, if the model is very accurate, for example, if you're able to get a model close to 95-98% accuracy, as I said, we might even skip a physical testing. We might rely more into the system simulations approach. The last but not least, making a single ecosystem is really important. We need to have a very robust ecosystem where we are able to model multiple systems into a single environment. I think GT is one such tool which helped us to develop multiple systems into a same environment and find the interaction effect of all these systems and find out the best optimum performance which we can deliver from the systems. So the add on top of these integrated systems is the data and the data lake which we are having about our customers and our products. So with these data and the data lake, we'll be able to improve and increase the robustness of a simulation, and thus we'll be able to have a very good model which can be deployed across different variants. So I think I come to an end by saying that the system simulation helps us, and also I think it will help everyone a lot in improving the model, and wishing you a great 2 days upon with the various presentation lined up from the team. Thank you.